Welcome back to Pentagramprime, everybody. In today's episode, we will be discussing Newton's method. This is an iterative process for the function f of x, where we are looking for the root of f of x, and it is specifically for the case where f prime of x does not equal 0. And essentially, it involves successive iterations of a variable x sub n using the function and its derivative to close in on a value for the root. In this example, we'll be solving sine of x equals x for x, of course, being in radian measure. A little bit different if it's going to be in degrees. Of course, this does not fit the setup of f of x being equal to 0, so we need to go ahead and change that. So what we can do is set sine of x minus x equal to 0. And then what we'll have is a case where our f of x is going to be equal to sine of x minus x. Next step is we find the value of f prime of x. Pretty straightforward for those familiar with Calc 1. But I'll spell it all out explicitly anyway. Having established our values for f of x and f prime of x, we are now in a position to set up the iterative formula for x sub n plus 1, and it is equal to, of course, x sub n minus f of x divided by f prime of x, in this case, sine of x sub n minus x sub n divided by cosine of x sub n minus 1. From here, we just need to make an educated guess about where we think the ultimate value of this iterative formula is going to land. Okay, so looking at the first quadrant of the unit circle, we can see that sine of x is the projection of this line here on the y-axis, and the value of x is the arc length going up along the unit circle here. The value of that arc length tops out at 1.57 radians. Red. Yeah, 90 degrees. And we can make an educated guess as to where these two items are going to be equal. We just know that it's going to happen somewhere along this arc. And since 1 lies somewhere between 0 and 1.57, why don't we go ahead and guess that it's going to, our starting guess will be x sub n equal to 1. It's not exactly where we need to be, but it's close enough for now. Okay, so having established that we're going to use x sub n equals 1 in the first iteration for, of course, values of f of x equal to sine of x minus x and the derivative as previously described, we get the following formula for x sub n plus 1, and this will require us to insert the numbers for sine of 1 and cosine of 1. is very important here to make sure that if you're using a calculator, it is set to radian mode. And since I know you love my camera work, I'm not going to make you watch me fill in all these numbers in slow motion. All right, having inserted our values for sine of 1 and cosine of 1, we crunch all of this and be careful with your parentheses and all that. Should come up with a value of approximately 6.552. Now, how many digits you end up carrying through each iteration is kind of a matter of personal preference, but through each iteration, you should start to see the numbers start to coalesce and get steady. So, okay, so we're moving on to n plus 2, and as you can see here, I inserted the previous values for x of n plus 1. And now, in spite of the fact that I'm the one teaching the lesson, I want somebody to tell me what I did wrong. I don't care if it's not my job or not your job. I want you to tell me where I messed up. Okay. Well, yeah. Fact is, this is actually supposed to be. Get rid of the minus sign. 0.552. Okay, a little messy, but I'm doing that because one of these days you're going to be on a caffeine bender and you're not going to always be thinking about what goes where. And if you end up on an 11-page assignment, it's very easy to make mistakes. And I'm pointing this out because it's very important to go back and check your work. I cannot stress that enough. Everybody I know, no matter how many years they've got in the field of mathematics or physics, you will eventually misplace a minus sign, misplace a variable, and you got to look out for stuff like this. So having cleaned up my formula for x of n plus 2 and plugged everything into the calculator, we get this thing approximately 0.4336. Got that down here. As I've said, the amount of accuracy you want to carry through each step is kind of a matter of personal preference. If you do it right, it should all come out in the end. So now we're going to move on to n plus 3. All right, so grinding out a formula based on n plus 2 equal to 4.336. We come up with a value for n plus 3 equal to 2.882, somewhere thereabouts. Anybody starting to see a pattern yet? No? All right, those of you who are familiar with the derivation of the derivative of sine of x know where I'm going with this. All right, moving on to x of n plus 4. Yeah, there's something I heard about the Bush administration. It was a little meme back before memes really existed. Bush Jr. said it's amazing how far you can get when nobody has any idea where they're going. Oops, I'm not supposed to talk about politics in my podcast. Oh well. Anyway, 0.1919, and moving on to the next iteration. Oops, did I just talk about politics? Yeah, that's the thing about some of us math guys. We have a very liberal bias. Anyway, n plus 5 gives us a value of 1.279. Oh dear. Did I just catch myself talking about politics again? That's the thing about us math guys. I'm so data driven, liberal. Anyway, x of n plus 5, 0.1279. Destination will become apparent shortly. Our sixth iteration has us at 0.0852, and I like to think the zero means there's the new zero means there's no need for a punchline. But what I'm going to do is I'm going to go ahead and do a couple more iterations on my own, and then we'll discuss where this thing ends up. Okay, this took a few more iterations than I wanted it to. Ended up going out to x sub n plus 12. But I'm glad I did it because, as you can see here, we're dropping another decimal place. We're down to an anticipated x value of 0.0075. And on a long enough, I was going to say time scale, but both time scale iterations, either way, could be here all day doing this. You find that really the sine x and the x approach the same value as x goes to 0. And this also leads to them having similar values, which is necessary for deriving the derivative of the first derivative of the sine of x, which is somewhat of a geometric derivation if you've ever gone through it. Um, so that's basically it. We've taken a um, so while this wasn't the most complex example I could have given you, I hope it did illustrate the basic principles, and we did see that indeed sine of x equals x as I was going to say x approaches 0, but it also works analytically for x equals 0 itself. And this technique, Newton's method, works for all just about any manner of algebraic function as long as it has a non-zero derivative. Use it on exponentials, polynomials, you name it. So, hope you had some fun, and until next time, this is Pentagram Prime signing off.